Real pleasure to be here. Thank you. So, as you probably are all aware, at this moment, every year, we're putting something like 25 billion tons of CO2 into the atmosphere. So that's 25 cubic kilometers if you compressed it to a liquid volume. Or another way to think about it that might be more useful is in the rich world here or elsewhere, think about something like a car a month of mass that each of us disposes of CO2 into the atmosphere. This is stunning. It's a geological force on the planet. This is more just plain material than we move in anything except maybe mine overburden. So the sheer volume material that we move around in CO2 into the atmosphere dwarfs essentially any other mass flow that humanity makes. The reason that we haven't dealt with this problem long ago is because we don't see it. But the problem is just mind-bogglingly big in that sense. Another way to think about just how big it is to compare it to the scale of nature's flux of carbon from deep underground to the atmosphere. One way to think about it is that the natural world is transferring carbon by volcanoes and outgassing in various places, transferring carbon from the lithosphere to the atmosphere. And it's doing that at a rate about 30 times smaller, and maybe more than 30 times smaller, than the rate at which we're now perturbing the system. So we often think of humans as some sort of perturbation to natural systems. We're not a perturbation to this system. We have completely overwhelmed it. We're doing this into a very thin atmosphere. This is the atmosphere seen from space. It's a very narrow, thin layer. And that's the layer into which we're putting these 30 cubic kilometers. That was if it's liquid volume, 1,000 times bigger if it's gaseous volume, with the consequences that we have all heard about. And I think one really simple way to visualize those consequences is that if we keep doing what we are doing, we will have the amount of carbon in the atmosphere similar to what it was last about 55 million years ago when there were alligators in the high Arctic. That transition took tens of millions of years to get out of as we cooled down to the current state. We are talking about warming it up again, putting that much carbon in on a time scale of my children's lifetime. That's the path we're on right now. So we could stop. Forget about geoengineering. This is a choice we're making. And now that most people know about this, it's a conscious choice. So let's just talk about how we could stop to just illustrate that this is doable. I'm going to talk about electricity because if you made me climate czar, that's where I'd start, and I think that's where most sensible people would start. And the reason is it's 40% of global emissions. They're the easiest emissions to manage because you can mix and match solutions, which is not so true for transportation. And they're probably one of the cheapest places to squeeze emissions. So with strong, cost-effective policy, we could realistically decarbonize most of the world's electricity production on a time scale of, say, a couple decades. And I would say the technologies that you'd start with seriously, these are things that you could actually start building right now at costs that are less than a factor of 2 above the way we now make electricity. And that's the cost when it leaves the power plant. The additional cost to you, because you've got to add on a bunch of other costs as a consumer, the additional cost is considerably less proportionally. So I think the serious things are wind power, nuclear power, coal with CO2 capture and storage, or central station thermal. There are a bunch of other things, but those are the things you could really do at scale now. Would it cost a lot? We were just talking before about the fact that it costs billions. Well, billions doesn't mean very much because lots of things cost billions. I think one way to think about it is this costs about as much as the cost of all other environmental controls in rich economies, which is a couple % of GDP. That's not the cost versus benefit. I think we get enormous benefit from the environmental controls we have, but that gives you a sense of what the costs are. It's a bit bigger than current military spending, less than Cold War military spending. It is much less than the cost of healthcare. There is simply no rational doubt that if we wanted to, we could do this and have an economy that looked much the same as it did. That's if we want to do it in a serious way. If we had to do that, have to get beyond this kind of goofy, phony war that we're in right now, where we are installing gigawatts of solar power in Germany and calling that success, while we're still building uncontrolled coal-fired power plants in Europe, arguably the place in the world that's most serious about climate change. That fact alone is the single fact that most clearly illustrates that humanity is just not dealing with this problem. They're just talking about it. I am not saying we should do geoengineering because we can't deal with emissions. We can deal with emissions. But dealing with it would require a really ruthless focus on cutting CO2 cheaply and effectively in ways very different from what we're doing now. So let's say we do that. Are we out of the woods? The answer is no. And there are two principal reasons why climate change is dangerous, if you like. And one of those has to do with the uncertainty of how much climate change we're going to get for a given amount of carbon in the atmosphere. And the other has to do with extraordinary inertia in the system. And these are really the key of what makes the climate problem dangerous. So let's talk about uncertainty first. The simplest way to think about it is this nice little wheel you see on the left that MIT climate change group has developed that they think of as a roulette wheel. And it's important to say that we might get lucky. We might put billions of tons of CO2 in the atmosphere and see climate changes of order a degree centigrade globally. And for some of us, that would almost certainly be a benefit, and it certainly wouldn't be a terrifically terrible thing. That's not a very likely outcome, but it's possible. We might get unlucky and see really spectacular climate changes, spectacular on a geophysical sense, as big as the glacial, interglacial transitions, things that would commit us to raising sea level by tens of meters over the next few hundred years. More likely, we'll come out in the middle, but we don't know which it's going to be, and we're not going to know until after we've made the decision to put the CO2 in the air. You see on the right some early thing that Granger Morgan and I did in the early 90s. We asked 15 of the world's climate experts in day-long interviews how sensitive the climate was to doubling CO2. That was because the IPCC at that point had a very narrow view of the uncertainty range, and this paper helped to change people's view about the uncertainty range. But a key thing was at the end of that day of asking these, really the world's best experts, we said, let's say we come back to your office 15 years later and you've been made czar of all climate research and all the research money was spent just the way you wanted it, and not only that, more research money than we have now, how much would the uncertainty have narrowed? And the answer was not much. And that was the answer they gave us 15 years ago, which has proved to be the right answer. And so we have to make decisions about risk without knowing exactly what's going to happen. So that's uncertainty. This is inertia. CO2 has a lifetime like nuclear waste. It is completely unlike pollutants like, say, sulfur, where the generation that spends the money to cut emissions sees their air get cleaner. Once you put CO2 in the atmosphere, if you don't do something about it by taking it out later, we'll talk about that in a minute, you can more or less think of the climate change impacts of that CO2 as lasting forever. 10,000 years later, you still got a half to a third as much climate change as you have at the peak, the day the coal-fired power plants turn off. And just to give you an anchor, this isn't a plug for nuclear or against it, but we have an idea that nuclear waste lasts a long time. In that same 10,000 years, the intensity of nuclear waste is down by a factor of 3,000 compared to when you pull it out of the reactor. Let's also think about the extraordinary inertia of policy. So let's say that governments suddenly get serious, get out of the kind of phony war mode about climate change and really begin to do something. Impose a high carbon tax with recycling, income recycling, and put a bunch of money in R&D and really force the system to cut emissions, which, as I said, we could do. So after a while, you start to build some low emissions infrastructure, because we're not going to solve this problem, especially not with 1 billion people who don't have electricity. We're not going to solve this problem by cutting use of energy. We're going to solve this problem by changing the way we make energy so that we don't put CO2 in the air. That requires building a lot of expensive infrastructure, whether it's wind power or solar power or what have you. But building the infrastructure, starting to build it, doesn't instantly do anything. It's only once you've built up a stock of infrastructure that you've reduced the emissions. That's the amount of CO2 going in the air each year. But doing that doesn't help climate change immediately. You only get the benefit of helping climate change once you've reduced emissions for long enough that the concentrations, the amount of CO2 in the air, is down. That is an enormous time delay. The combination of those two things is the central reason this problem is dangerous. Because we're not sure how serious the climate change is going to be, and there's some low probability chance it will be very bad, and there's enormous inertia, so we can't just stop the problem suddenly. That's the core reason why the climate problem is dangerous. So given that, one of the things that I and others think we should talk about and research, but not do now, is think about ways to engineer the climate. And the reason is that at some point, and that point could be today, even if we cut emissions instantly, we would still have enough CO2 in the atmosphere to cause a problem. And we need to think about how to manage the risks of that CO2 in the atmosphere. At least the main kind of geoengineering which I'll talk about is not principally a substitute for cutting emissions. It's something to do to limit the environmental impacts of the CO2 that's in the air. So just to give you a kind of a taxonomy, geoengineering is something we do to the climate system that changes the link between human actions and the impact of CO2. Of course, it's important to say that while we can adapt, natural systems can't, or don't in the same way. There are two completely different things that go under the name geoengineering, and I think in thinking about it and discussing it, and even I can tell you without revealing very much in the work of the current Royal Society panel, it's easy to get tangled up by considering them under the same name because the consequences and ways to think about them are so different. So one thing is this solar radiation management, this idea, which we'll get to in a second, that you could shield some sunlight and it would get colder. There's a whole bunch of ways you might do that, as you can see, but all those ways have the property that they are very fast, they're very cheap, and they're very uncertain, but they do very little about the carbon in the air. There are a whole bunch of things we might do to take CO2 out of the air, ranging from high-tech ones, like this direct capture of CO2 from the air, which I'm working on, to less high-tech ones like biochar, which is currently a hot topic, which may or may not be all that useful. But these are all things to get carbon out of the air. And there's no question that getting carbon out of the air is a good thing and essentially risk-free. So some of these things may have local environmental risks, but there's no risk associated with getting CO2 out of the air. After all, that's the whole point. So these two topics are very, very different. Let's talk a little bit about the first one. This may sound like hubristic overstatement, and all discussion about geoengineering is kind of tinged with concerns about scientists' gross hubris about how they can manage the world. And I hope to convince you that it makes sense to think about that in a way that's not hubristic. But let me make the statement. There is no scientific doubt that if you put aerosols in the upper atmosphere, it will get colder. There's lots of doubt about how well that will or won't compensate for CO2 in the air, or about what all the various side effects of it will be, but there's no doubt it will get colder. And it will get colder in about a year. And the reason we know that is because volcanoes had done the experiment for us. So when that volcano, Pinatubo, put 10 million tons of sulfur in the air, it got colder in a year, and that's been true of all the other volcanoes we've seen in the historical record. There are a whole bunch of ways, which I will skip over except to kind of wave my arms and say that it's complicated. There are a whole bunch of ways that we might do this that are more sophisticated than just putting sulfur in the air. But as yet, there's been essentially no serious scientific research. So I can tell you very little about what these ways would cost, or which ones might work better or worse, or in particular have more or less environmental impacts. But for those of you who like to think about numbers, I want to point out one number that has to do with the leverage of science and engineering over the planet. And I'll come back to that in a minute. And that one number is this number here. So one pound or ton of sulfur in the stratosphere offsets roughly 300,000 tons of CO2 in the atmosphere. I'm not claiming it perfectly compensates for the effect. It does not. But that gives you a sense of the leverage. And if you're thinking this is going to be a big amount of sulfur to rain down on us, this is actually a few % of our current sulfur emissions. So that is not a concern. There are lots of other concerns about this. Just to give you a teaser, one particular fun idea I've worked on personally is an idea that builds a little bit on this technology, and it has to do with the fact that you can actually levitate particles in the upper atmosphere due to unequal heating of them. The actual effect doesn't involve unequal heating, it involves some other physics trick, but this is the one that works in interstellar disks, and it's one that's relevant. And the bottom line is those of us thinking about this believe we have a way to levitate small particles, and indeed it turns out nature almost certainly already does that. It has a layer of levitated particles at 100 kilometers, and there might be reasons why doing aerosol, that aerosol fine particle, geoengineering the stratosphere using methods like this or any number of advanced methods might have less side effects or be more controllable than just imitating volcanoes, but we won't know it if we don't do some research. Particularly, we won't know how it won't work. Another thing that, just to sort of give you a teaser to the stuff that I do, I can talk about it because I know about it, that's fun, is I spent a lot of effort, actually I have quite a large number of people right now working on ways to capture CO2 directly out of the air. That's that other class of technologies things that are expensive and essentially certain to work in the sense of solving the problem if you really did it, but not at all certain to work in the sense that I can't claim we know for sure we could do this at an interesting cost. There are about 4 or 5 groups with little startup companies building air capture efforts now in the world. The particular focus of our group, and this gives you some idea of why we think air capture might be interesting, but the particular focus of our group is to build air capture technologies as much as possible on existing industrial processes that can be scaled up with kind of classic chemical engineering scaling so we could actually do it soon and cheap with very low technical risk. We're building on technologies from the paper industry and quite conventional chemical process technologies. This is one of the standard slides I use in the big air capture talk, and these various things around here are all pieces of hardware that exist in the real world today, and we're essentially figuring out how to combine those pieces of hardware to build a commercial air capture system quite soon. So I'll skip over that. I want to come back to this issue of leverage. One claim that's sometimes made is, why worry about geoengineering? Because we're already doing it. So people will say that we've already been engineering the planet by putting all that carbon in for a century or two, and so we shouldn't get too worked up about the idea of engineering the planet. I don't buy that argument. I think that intention matters just as it matters in common law. And there's a difference between deliberate engineering, doing something with the intent to figure out how to most effectively lever the planet, and just making a mess. So I think what we have been doing was producing energy that we wanted to run our civilization. And as an accidental byproduct, we've been perturbing the climate by putting a huge amount of carbon in. It's not an accident anymore. We know about it. Indeed, we've known about it for a very long time. So one thing you often get if you're the general public and you haven't done too much more than read a few stories about climate change over the last decade is you may think that the science of climate change is new. You may think, there may be climate skeptics in the room, there's certainly lots of climate skeptics around, you may think that this is something environmental scientists just happened to cook up in the last 10 years to try and convince us that industrial capitalism is a bad thing. Well, this is the report that got to President Johnson's desk when I was 3 years old. And it says essentially exactly the same thing that the climate science community says now. Because the core climate science that says you put that much CO2 in the air, you're going to have a serious problem, has been around roughly since the early 60s. And an interesting fact is that report talked about geoengineering. And indeed, every other major scientific report on what to do about the climate problem, like the MIT reports of the late 60s, early 70s, or the US National Academy in 1977 or 1982 reports, all dealt with geoengineering, but then it became taboo to talk about it. And only in the last year or so have we the taboos become unhinged, and now we're talking about it for better or for worse. And I have to say, I wake up at night sometimes wondering if it's for worse. So I'll ask few slides about 2 different ways to think about it. One way to think about it is to consider geoengineering as an alternative to cutting emissions. And there are some people who actually advocate this. They say, well, let's just keep ramping up the amount of CO2 in the air, and let's ramp up the amount at which we turn down the sunlight. And heck, plants grow better in higher CO2 atmospheres, so it might actually be a benefit. And we'll just merrily go on to the future. And since it's much, much cheaper to do this than to cut emissions, that might be a good deal. I think that that's just reckless nonsense for a bunch of reasons I can come back to in questions. But I think it's harder to dismiss this. So let's say we actually get serious about cutting emissions, which I hope will be soon, but I fear will not be. There will be some day, and maybe we'll have global celebrations, where we turn the corner, where the amount of CO2 in the atmosphere stops growing. Maybe it'll be 2072, maybe 2050. That'd be about as early as I could imagine it being. And on that day, we will have begun to turn the corner, as we have already turned now a few years ago for chlorine in the stratosphere. That's a major environmental problem we did solve, banning chlorofluorocarbons or controlling their use. So we're going to go over a hump. And the question is, would we like to minimize the environmental damage we do from the CO2 that's already in the air by shielding a little sunlight? And the answer to that, I think, is that's not so easy to dismiss. There's a problem. Knowledge that geoengineering is possible makes the climate impacts look less fearsome. When I don't have my geoengineering hat on and I'm going into Canadian or American politicians and trying to convince them to act on climate change, I, like every other climate scientist, say, you got to worry about that low probability, high consequence tail of the climate uncertainty, the idea that Greenland might just slide into the sea. And I use that to try and scare them into acting to regulate on emissions. But of course, if we know that geoengineering works, which we do not know, then that will look a little less convincing. And that's a problem. And I think that's the central reason why there has been a taboo about talking about this. And I think it's dangerous to talk about it, but nevertheless, I now feel that it's better to talk about it than not to talk about it. So the last 2 or 3 slides, some opinions. We need a serious research program, but it doesn't need to be big. But right now, we have essentially conversations about geoengineering dominated by a kind of blogosphere that's pretty non-scientific, and that's dangerous. Current understanding, and that's with every major climate model, about 4 or 5 that have been run on a geoengineering test experiment, indicate that geoengineering could, if done sensibly, lower the risks. That doesn't prove it's true, but that's the current evidence. I think you should treat it as a means of managing the worst impacts, not as a substitute for emissions reductions, but I'm wise enough to know that people like me don't make the decisions, and the science community should expect to lose control. And we need to do a lot of thinking about international governance and norms of behavior around both research and, should we have to do it, implementation of geoengineering. And I'm sure we'll talk about that later. I want to think about one more framing of this. There's an argument for why we should do research. Imagine a dichotomy. Geoengineering either works or it doesn't. Of course, it's not that simple. It's going to be in the middle, but just suppose it was that simple. So we expect either that it doesn't work or it works, and we find out after we do some research or try it that either it works or it doesn't work. The very worst case to be in is if we think it works and it doesn't. And I think that's one of the reasons, the fundamental reasons I think we should talk about it and do research now, is I feel we could slide into that in a way that's dangerous. Equally, we don't really want to be in a situation where we just assume it doesn't work and it does, because if it really did work reasonably well, we've missed an opportunity to limit the damage to ecosystems we might really care about, like the high Arctic. In closing, I just want to emphasize again how extraordinarily slow progress has been on this. The scientific understanding, both of the possibility of these kind of engineering solutions and of the underlying climate science, is very, very old. And yet, despite that fact, we're now sitting here in 2009 and are doing essentially nothing to cut emissions. I know a lot of you feel like you're maybe doing stuff personally, or your government may be talking a lot about cutting emissions, but I think the following is true. If you were a Martian who came down and just kind of went around the planet watching what people were actually doing with their energy systems, you would be essentially impossible to detect any real movement to limit emissions at the pace necessary to deal with the magnitude of the climate problem. I think that's a fair statement. That is not, we're not committed to that. That's a choice. So I really dislike it when people say we must geoengineer because we're never going to cut emissions. No, we can cut emissions. We should cut emissions, we must cut emissions, but we might also want to learn how to manipulate the system to reduce the risks of the CO2 that's already in the air. Thank you.